Okay, so today I'm going to do something a little different. So I'm not gonna do lead code problems this time, but I'm gonna actually start to implement a hash table from scratch. And I'm gonna start doing this in Python. And then eventually maybe I can rewrite it in another programming language I would like to learn. Maybe that will be either Go or Rust. I will see. Um, but yeah, let's first start with Python, and I'm gonna just chunk it up into different like video recordings, so they're not so long as well. Um, so this is something I wanted to do for a while because I wanted to understand a little more behind the scenes how it works. The different types of algorithms for handling collisions and resizing as well. Um, and perhaps, yeah, we will decide like what this hash table is gonna basically convert to. Maybe it's gonna be used as a cache or something. Okay, so the core components of a hash table, we have here like the load factor, the hashing algorithm. Then we have collision handling, and then there's like various types of algorithms for collision handling. And then we also have dynamic resizing. So for example, for handling collisions, well, we have like an overall theme here that's called separate chaining. And then we also have another strategy called open addressing. And inside open addressing, we also have like different types of algorithm to resolve collision techniques. I actually don't have much idea about them. I haven't looked at them in detail, but the idea is to implement some of these ones just to try. Um, yeah, and also like have like some kind of good logic to identify when do we need to resize the table, or if we need to like create other tables as well. I'm not really sure how that works, but I'm gonna explore it basically um, through like as time progresses. So in the first version of this I'm gonna start writing today. It's gonna have like a hash algorithm, and it's gonna have a very basic like a simple separate chaining approach to handle collisions. And the simple way of doing that is basically creating a linked list between colliding items, and that's it. So I'm not really going to create a linked list, but just use like an array, right? So then when two items have collisions, and then we, for example, need to search for a particular item, well, that will be like a linear search. So in this case, like our worst case scenario for insertions, or sorry, for like retrievals and perhaps also deletions will be linear search as well. So it'll be like constant time in worst case scenario, right? Because of hash collisions. And also like generally speaking, for example, like if we have here the hashing algorithms. So that is like one very important step. I'm not gonna, of course, implement one from scratch. Well, maybe in the future that could be interesting just to learn, but these are like solved problems. So there's two properties that like a hash function needs to guarantee so we can use it in a hash table. And it has to be one, it has to be extremely fast to compute. So it has to be like very low latency. And it should minimize collisions, right? Or minimize the duplication of the output values of that hash function. So basically it needs to have an equal probability of all outputs to occur. Like we cannot have like one output to be more probable than the other ones, because that will increase hash collision. So it's not evenly distributed in a probabilistic manner, right? So these are just some of my initial notes. I'm just like yeah, basically summarizing some of this. So okay, cool. So I'm gonna basically just walk through here, and most of like this information I initially got it from these two Wikipedia articles. So the first hashing algorithm that we will use is very simple. So it's basically this function, like the hashing function equals the input modulus the total number of buckets of the hash table. And then just for maybe simplifying this, like what I'm referring here to X is basically the output from a built-in hash function of the programming language that this is going to be implemented. So for example, in Python, they have the hash function. And then that particular hash function is also explained here. So they use so this hash function under hood uses zip hash. In case like, you know, we can take a look at it later how it works, but basically it's a new hash function that was added in Python 3.4, replacing the previous one. Because the previous one, basically the problem was that it was providing more hash collisions than it really wanted to. So of course this could pose security risks, right? Like some attacker can gain, you know, like take advantage of this vulnerability, and then you can like make some queries take longer than they should, right? Then that could be quite dangerous for like APIs that are search intensive or basically read intensive, for example. So anyway, that's the update. So it's here as well. So that's the basically the hash under the hood, what is going to be used for hash, the hash function. And basically the general flow, I'm going to diagram this really quick as well in the Jamboard. So basically the general flow is that we have a key of an item we want to add, right? So it's key value pairs, and we compute the hash, and then that hash maps to a bucket index. And after we have the bucket index, then we add that element, right? That item that's going to be like yeah, think about it as a tuple, which holds the key, the real key, not the hash one, with the corresponding value. So it's quite I mean, at a high level, it's quite a simple idea. So for example, if we have here like some diagram here of a table. It's going to have 4 slots. And then, for example, here, I can have these thing represented kind of like the indexes, right? So so basically how this works, right? So if we go to the Wikipedia, yeah. So with the constraint of uniquity. So basically, yeah, it's an array of length m is partially filled with n elements, right? And then a value x gets stored at index location, where h is a hash function, right? This is what I already explained. So I'm just gonna perhaps, let's see if I can copy this, I hope. Yeah, no, it doesn't copy it very well. Okay, doesn't really matter. I mean, let's maybe like this and like this. Okay, move myself here. Yeah, so basically we have here right an array of length m filled with n elements, right? So basically that's gonna be our bucket. So we're gonna have a main collection, and we're gonna basically fill it here with these buckets. I'm wondering why can't this? Okay, let's see if this is better. Another problem. Oh, okay, I think I'll have to like zoom in here. 50, 100. It's too much, but I think that will do. Okay. Okay, so basically the logic of this is quite simple. So we have our hash function, right? So we have our let's say we have first like an item we want to add, right? So we have like a key, and we can say it's like foo, and then the value is like 55, right? So when we want to add an item, basically, we're gonna compute the hash of this, right? Foo. So basically, it's gonna be hash, foo, and then it's gonna be modulo n, right? And then that's gonna be our basically our key. modulo n, and then that key is gonna be matched to some value in this bucket, right? It's basically going to be an integer. So key is an integer. And then this is also known as, so if I go here to the hash function resource, integer, let me do Control F, integer. Integer variable length. Maybe it's actually here. Let's see. Integer. Shit. I accidentally. Okay. Where is it? Still hash function, sorry. It's hash table. So let's do it again. Integer. Yeah, constraint hash functions are based on the integer universe assumption that all elements of the table stem from blah, blah. So here we have the integer universe assumption, right? The schemes of hashing used an integer universe assumption include hashing by division, hashing by multiplication, blah, blah. And then it says here, however, hashing by division is the commonly used scheme. So that's the one we're going to use. That's the formula we already saw, right? So we have the hashing function equals n modulo m, right? So this is what it is. Hashing function equals, or the key basically, right? The key or our hashing function equals the hash of the key modulo n, right? Which is the number of buckets. So in this case, 1, 2, 3, 4. And then of course that will be an integer, right? And let's say like that integer will like map to some index, right? So let's say like this will map here. So let's say this will be index 0, 1, 2, and 3. So what that means is that this object will then be added here. So we will add this object here and here. So that's the general idea of this. And for example, like the thing is that if we, for example, have another object, right? Let's say it's like, instead of foo, it's like, fa. And then we have like, another value like 65. It could even have the same value. It doesn't even matter. But if for some reason, if for some reason the key, right, like the hash, if there, there's a hash collision, which basically means that we hash this, and the output gives you the same number 2, right? That will be like a hash collision produced. Basically, this object will also be added to here. Will be added to here. And of course, you can imagine like if this is like very write heavy and there's like millions of writes, and there's quite a high probability, or like this is not really such a good hash function, like we could have like bucket number 2 like overloaded with perhaps thousands or millions of elements, while other buckets don't have so much load. So this will basically cause like for this bucket that we will have to do linear search if we want to like retrieve a certain element or delete a certain element from the bucket, right? Which will be extremely expensive. But that's basically how at the moment we will basically handle collisions. Is basically just adding another element to the same bucket. So this is basically like a high level overview of what's going to happen. And then the other thing that we're going to handle is if, for example, for some reason we are going to add the same element, right? We're going to add the same element, That's gonna be here. And then, of course, it's repeated. What we're gonna do in those cases is that we're gonna update. So for example, for some reason, this has another value like 65. We're gonna take the existing element and then modify it to 65, right, instead of 55. So during insertions, if an element with the same key is encountered, we will basically override its value. I mean, we can like throw an exception or something, but I mean, I think that's just an implementation or a design choice. Like we can override its value, for example. So, okay, so let's get this started. So I'm going to create a main.py function, and then the usual if name equals main, and then we can print like the hello world. Our hello world thing. And then I think we can terminal, new terminal. I want to do a git bash. Okay. So let's run this. So Python main.py. So yeah, we have our hello world thing ready. Okay, and then we are going to create here another file. Why not just in the same, just for simplicity, we can just call it, for example, or I just called it lookup.py. So I named this little project, so lookup.py. And okay, so lookup.py. So basically we are going to have this as a class. We can say class look up, and then we're gonna have def with constructor. Okay, and then we're gonna have our size. So we can start this like with some initial size, I believe. So self.size, and then we can like start with something small. Okay. Maybe like, yeah, let's create here a variable with 10. Can say size. And then we can have our buckets, and then that's basically going to be it's gonna be a list, and we can say list comprehension. So for self.size, so this is basically going to create our buckets, right? So it's going to create 10 buckets, right? To n. Okay. And then after that, we need our methods. So we're going to say def. So we're going to have our hash function. Here we're going to have our key. And I think, yeah, the key could be anything. So I think we have any. So I think we have from typing import any. And here we will add, it will be a list. And then it will be a list as well. And then it will be of type tuple. And then we're gonna say from typing import lists as well. So it's gonna be a tuple because, right, we're gonna add a tuple. Right, so it's gonna be the key and the value. Okay, so we have here, okay, key. So then we are going to do the following. So it's gonna be return hash key, and then we're gonna say modulo self.n, sorry, self.size. So that's gonna be basically the key here. So maybe we can do like some reference to the hash function here. It's gonna be hashing by division. So we can maybe say hashes the key based on the, okay, copy it, based on the integer universe assumption using the hashing by division technique. Okay. So here it is. So let's yeah, why not? Let's just test this and see how it's looking. So we can have our so from lookup import lookup, and then we have here, we can remove this, say, oops, you can say lookup equals nothing here, so we can say lookup dot hash, oops, lookup dot hash equals, so a key, so that let's say foo. Okay, so let's print this, let's print, so we can say hash, and then I'm gonna print hash. Okay, this is saved. So now let's run this. So it's 6, right? So this will map to basically a bucket with index 6, right? So it's working here as expected. Okay. So after this, we will need to define our, so def insert self, and then I'm gonna say pass. Then we have to say def delete. And then we need a get as well. Okay, so those are the 3 operations that we need. Okay, so let's start here with insertion. So we need to insert a key that can be of type any, and also a value, which is also of type, can be any value. Any value. And I'm curious to know, like, if Python, yeah, probably, well, when it's like, you know, when the interpreter is running through the code, I guess it will do some type inference on the any, so it could check for equality, I guess, but let's see. Okay. So this will return, of course, void or none. Okay. So let's do this. So we are going to have our key. So we're gonna say the same hash self dot hash. And we are going to say key. This is gonna be our key, right? And of course, this should return here an integer. And then after that, this will give us like the index here. Right? So if we have, for example, self dot buckets, then we have our hash. We have here our hash, right? So then this is the target bucket. This is our target bucket here. And of course, that's gonna be a list of type tuple. And so now we're gonna do what I described here. Where is my other window? Okay. I'm gonna do what I described here, which is handling, like if the items have the same key, we're gonna like override the value. But okay, but then of course, if it doesn't, so we're gonna have some return statement. Well, yeah. Blah, 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 blah. So let's just say down here, which is like the default value. So this is how we're gonna basically handle the append. And we're gonna say key and value. Okay. And now we are going to say for item in target bucket. And of course, this is going to be a tuple. And we're gonna say item can actually, I forgot here. Let me just do an experiment really quick. So if I have a tuple here, T, and then I have, for example, the value here. What happens if I do print T0 for key? Should give us AA, let's say. Yeah, okay, cool. So we have here. So if item 0, well, we can say maybe existing key. So item 0, right? So if existing key equals the key, we're gonna update this element, right? The value. So item 1 equals value. And if I run this, for example, item 1, and then I go print T, sorry, print item 1, and then if I go T equals, let's change it here, like 1, and let's print it. Would work. Okay. Tuple object does not support, yeah, because they are immutable. So let me see. How can we do this in a better way? I want to hide this graph. Assign new value to tuple. Let's see if there's a way. Once of those, you cannot change its values. Tuples are unchangeable or immutable. Yeah. Tuple into a list, change the list and convert the list back to a tuple. Yeah, I don't. No, that will be an overhead though. Or, maybe let's try something different. Should we use a tuple? What happens if we also just use like a dictionary, key value? Or an array with 2 elements? Not sure what would be the best thing. Well, let's try it. Why not? Let's try this. Let's try this. Why is this complaining? Okay. I'm gonna try this for now. Implementation can always change as well. But let's just so we so here, so let's just say key will be key, and then we can say value will be value. Okay, so now we are gonna say, okay, existing key, so we're gonna say, we can just say like key equals key, so we're gonna say value equals value. Okay, and then after that we basically return. So this is going to happen, and then of course, and then if there is a hash collision, so when there's a hash collision, the key is not the same, but the hash value is the same. So handles hash collision. So oops, collision. I think that's how you spell it. So key is different, but hash key is the same. Okay. So we can call this like V1, version 1. And then, okay, then this will iterate over all the items in the bucket. We'll check the key. So if the key is equals, we will update the value and then return it immediately, right? Because we're not gonna add, basically that prevents adding that's the idea. Because the key will be the same, so we don't want to add items with the same key. So does not add items with the same key to the bucket. Instead, it updates the old value, the new value. Kind of obvious, but I'm just gonna leave it here for clarity. Okay. So this one is finished. So let's test as well. Let's test this. So, okay, I'm gonna delete this. So hash, and then one thing that can be done really quick is that we have a search does not equals, so hash is larger than or equal to 0. I think we should never get like a negative hash because we're doing modulo, the modulo operator. So let's just run this first. Main that by. Yep. So it succeeded, and then we can do another little test. We can say we're gonna add. So let's say we can call this item A is gonna be actually lookup dot insert. So we're gonna have the key, and let's just call this key again like foo, and then value that's 55. Okay. And now let's just print this actually. Let's run this for a moment. Okay, cool. No error, but I'm gonna print. So let's print lookup dot buckets. So here we have that mapped to, seems like the first bucket, key foo. So we have to say, for example, we can assert lookup dot lookup dot size equals 1. Oh, actually, no, not lookup dot size. I want to keep it, be able to keep track of the number of elements. So why not? I mean, we have this size. You know what? I'm just gonna call this length or the size it can store. Yeah, I'm gonna call this actually length. I think will be a better name. And then size. We should keep like that. Well, let's do that for now. Size equals 0. And then here, let's just increment the counter. Why not? Plus equals 1. And then we could decrease the counter. Pass. Okay. So let's do this. So size has to be equals to 1. So let's run this again. Yep. So it equals to 1. Perfect. So we have that working. And now let's try adding a new item here, right? So this should still equal to 1, right? Still equal to 1. So let's run it. And yes, it still equals to 1. And let's just print. Why not? Let's print. Oops. Lookup dot buckets. So let's print this thing. So yeah, it's working. So 65, it was below, it was 55 before. So yep, it is working here. Okay. Perfect. I don't know, like how I can simulate perhaps a hash collision. Probably, I mean, we have very little elements, so that could be possible to easy to simulate it. But anyway, let's I'm gonna keep this here. And let's do the deletion. Let's now do the deletion. So we need to delete an item at a certain key. So we're gonna do the same thing. Maybe like would even be good to do a like a get bucket. So we can say get def get bucket self, and then we can say key, and we can like do this we can do this. And we return the bucket. Let's do this here. These are the returns. And okay, so get bucket. It should be like this as well. Rename hash. Okay, so get bucket. So we can basically replace this and we say target bucket and key. And then I can remove this, removing duplicate code. Okay, perfect. So then I need to do the same here. So this is the target bucket. And I also need the key here. And oops, key any. Okay. And then we are going to loop. Of course, like if there's only one element, it'll be easy. I mean, it'll just loop once. So let me copy this thing here. So I don't think I can delete while this thing is iterating through the bucket. So let me do something. I want to check because if there's one, we can just say pop. So we can say if length, so we can just check the length. So we say if length equals 1. So first of all, we have a base case actually. So if length equals 0, maybe this should return. What should this return? Like a Boolean, maybe? So if length equals 0, return false, perhaps. Like nothing was removed. Maybe I can store this in a variable. N equals this. So if n equals 0, return false. Then we're gonna say if n equals 1, we pop. So we pop. So there's target bucket, but we can immediately pop it. This returns an element. So remove first occurrence of value and raises a value if the value is not present. You know, I forgot this API for a moment. Python, let me just Google it really quick. Python remove. Let's see, I've looked at it before. Remove 9. But it removes 9, but I don't want that. So Python remove it's index. Let's see, looked at this one as well. That's by value. Oh, okay, okay, I see. Okay, so we can say del first one, and then we can, yeah, just say return. And if not, we can do this. So we will, if it's key, we remove, but maybe we can say index to remove. And I think I'm going to say enumerate enumerate. And then I'm gonna say here I equals I, and then we break of the loop. And then here we'll say target bucket dot delete at index to remove. And then we delete like this. And we can return, oops, this will return true, and this will return true. Perfect. Okay, so target bucket, okay. So I have to pause this a moment. Sorry, I have some, just give me a second. Okay, so yeah, I'm back now. Yeah, so okay, yeah, probably noticed a different table. So yeah, they brought a table by surprise. So here it is. Okay, so let's get back to it. So this, yeah, I think I was going to do some unit tests. Okay, so let's do this. So let's look up dot delete, and let's do key as foo, and then we have to say self dot size, reduce size by 1. So let's now do this lookup size equals 0, and lookup has no attribute hash. Ah, okay, why? Oh yeah, of course, because it's private. Okay, yeah, I'm gonna comment this out. Commented this out here. I made it private, that's why. So okay, Python.main. Okay, so assertion error. It didn't delete. So let me see R. Let's print R. Let's see what's the output of R. So let me do, say lookup. I'm gonna print this lookup. Buckets. Okay, sure. But then why look up that size? Now, let's see size. 1. Look up that size is 1. Why? Oh, I see. Oops. Oops, oops. Because I have to do this here. That's why. Very good. Okay, perfect. So let's try this again. Yep. 0 and true. Perfect. Yep, yep, yep. So we can call delete result. And of course, this will have to be delete is true. Okay, tool. Okay, so let's run it again. Okay, nice. Okay, so it is deleting as expected. So now let's try to do the other test where basically this will return false because we have 0. Actually, yeah, this will be 0 here, target bucket. So we can't delete anything, of course. So now we can, let's check this again. Down here, so we delete foo, and then we say assert is false. So let's run it again. And yes, so base case is tested. This one is also tested. And now, of course, we will need to test this one. Yeah, that'll be a little more tricky to test, but let's keep going. So let's implement the get one. I'm wondering also, there's like some examples. Why is this? Okay. I'm gonna delete this. There's also some examples here. I'm wondering if. Okay, I want to see some hash collisions. John Smith and Sandra D. I'm wondering if those actually have hash collisions. Yeah, not sure. It's probably diagrammatic actually. So never mind. Okay. So I'm gonna now do the get. So we also need a key, any. And I'm also gonna have the target bucket. And it's gonna give us the value. So also gonna be any for now. Okay. So of course, what happens if the key doesn't exist? So we have, and I'm gonna say also none. So again, we can have this base case. So we can have here n, and then of course, where the bucket is empty, we will return none. And then we have this as well. We can just say, okay, if n equals 1, we can just return the first element. Otherwise, we have to loop. So loop until we find with key. We have to loop through the array. So we can say for in target bucket. So if item key equals our target key, we return the value. So we say item value. Perfect. And if we can't find it, we have to return none. We will return none, right? So if item not found, bucket none is, well, maybe we can just actually do the f-string documentation here. So get an element by a specified key. So then we say returns. We can say none if this. Otherwise, value is returned. into a value. Okay. So we have this, perfect. So we can also do something similar. So delete element by the specified key, returns true if the deletion succeeded, otherwise false. Okay. Okay, perfect. So I think for now, this is it. This is like, yeah, good enough for this implementation. Then of course we will need to implement the resizing. So that will be left def resize. And this will be basically as to do. And we also need a more sophisticated handle collision, handle collisions. And also we will say to do. And that is basically it. So let's try also to get a value here. So lookup dot get, and then we're going to say the same key pull, and we can say get result, and we have to assert get results is none. And perfect. This succeeds. So now I am going to add again. So let's do another test. So we have this insert. And then we can say, for example, insert like this thing. And then we will say assert that size equals 2. And then after that, we can say, for example, get result. We can look at for example, for this one. And we will assert that it's not none, is not none. So let's run those tests. And boop, they succeed. So this is, yeah, I think this is good enough for the first implementation for this custom hash map. So I'm gonna commit these changes. So I should have installed like some linter as well. That's fine. Okay, we can do it later. So did that. So V1 implementation and for custom hash table is complete. Okay, so now git push origin master. Okay, maybe because I haven't added it. Just a second. So let me. We'll do that in a second here. So GitHub. My profile. Okay. Lookup. So I haven't added it. Okay, so let me just, I think I just need this line of code. Now let me try it again. Yes, cool. Okay, so yeah, so this is basically it for now. So I'm gonna keep yeah, working on this and making it more sophisticated. So this is it.